Today, I'm taking on a challenge. Now, I've got this beautiful studio I've had the luxury of working in for the past 10 years, but I'm currently building a new one. So I've only got 9 to 12 months sort of left in this one. I might have both of them running at the same time. I don't know, but I want to make this room sound even better than it currently is without breaking the bank. I mean, don't get me wrong, this place already sounds great, but I made some mistakes in its design 10 years ago, and I can't change the structure now. It's no point doing any major changes, but I'm going to try and improve the acoustics without spending any big money. And guess what? I want to take you guys along for that ride. I've got spreadsheets, calculators, and I'm going to take tons of measurements. We'll explain the theory behind each of my attempts to improve the response of this room. So if you've got a pair of speakers and you work on music and it exists within a room, well, this video is for you. So don't forget to hit that like button and subscribe so you don't miss out on all the action, including the subsequent 2 videos I'm going to be doing in this series. So let's look at the brief. This room's modes and responses are dictated by the room's dimensions, just like your room will be. Now, this room's internal dimensions are 4.8 meters long by 4.4 meters wide at the front, 4.2 meters wide at the back, and a 2.7 meter suspended ceiling with a reflection-free zone design. That was my concept, which at the time I believed would spread the room modes evenly. The problem is low frequencies completely pass through the 6 inches of porous absorption that fill the internal frame and bounce off the external wall boundaries and create a modal spread between the X, Y, and Z axes of the outer frame of this studio, because this is a room within a room. And those external frame dimensions are almost identical length and width-wise. And even though in the corners my bass traps are 800 millimeters deep, or 31 inches to you Americans, and in the front ones they're 600 millimeters deep, or about 24 inches deep, I've learned as of recent, porous absorption, even with a relative low gas flow resistivity, is a game of diminishing return. And even in addition to that, that sort of porous absorption is still somewhat reflective at really low sub frequencies. So this can cause some pretty gnarly room mode issues in the subs. Fortunately, these room mode issues aren't horribly exacerbated, as the external walls on the outside of this internal frame are hollow drywall, and a lot of those sub-frequencies just pass through and don't compound on the decay time I experience here in my listening position. So, what I've got is a plot of the room in the current listening position, current speaker position, and you can see there's about a 104 to 90 to 104. That's a plus minus 7 dB deviation. I really want to be within a plus minus 6 dB deviation in these low frequencies. That's 1/24th octave smoothing. And you can see that you can see a clear room mode. That's the 35 hertz there. That's the 4.8 by 4.8 X and Y axes stacking on one another quite a lot there. And these room modes here, here, and here are completely fixed. Now, if you're wondering how you calculate a room mode, the first and most strongest modal resonances are half the length of the distance of your X and Y and Z axis. You can't change or shift these room modes without physically changing the external dimensions of the room. I'm fortunate in the new room design, I was able to work with a draftsperson and get those dimensions to exactly what I wanted on the external frame, so the room modes were evenly spread. However, in this room, I can't do that. So my theory to improve the response is to leverage SBIR, or speaker boundary interference response, to create peaks and nulls in opposition to the room response, which I've plotted here. Now, speaker boundary interference response happens when the sound from the nearest surface or boundary to a speaker reflects back to the speaker and causes a comb filter to the response of the speakers themselves. Now, the distances we have to be critical and keep in mind are wavelengths of odd quarter fractions from the boundary, so quarter, 3/4, 5/4 wavelengths interfere with the playback of the speaker destructively, causing dips or nulls, and wavelengths of even quarter fractions, half a wavelength, a full wavelength, 8/6 or 3/2 interfere constructively, causing peaks in the speaker's response. Now, as I'm piecing this together, I'm realizing this won't necessarily change the decay in the response of the room modes. They're fixed. They're always going to happen, but it may help smoothen things out. And I want to preface everything with great skepticism, because this is all theory. I'm not an acoustician, and in application, what I actually plot might be different. So what I've built here is a calculator in Excel where I can input room dimensions and speaker positions relative to their nearest boundaries and plot the room modes, which are fixed, against the interference, both destructive and constructive, of the SBIR for both the X, Y, and Z axis. Here I put in my current speaker positions, as you can see, 73 centimeters from the front wall, 143 from the left and the right, and 125 from the floor. And what's this going to enable me to do is to make decisions on how I'm going to change these. So let's say I choose to make this 100. It changes my X-axis peaks and nulls here against the room modes. And my aim here is to plot like I have now, observe what can I improve by moving the X-axis or the Y-axis, and then plot again and then see, is what I predicted here improving the response in real life, and then make educated decisions on how to move and shape these speakers or change their position in the room. That's how we're going to be changing the response or improving the response of this room for free. That's the pun. Let's actually do this. This is going to be pretty fun. The first thing I want to check out is we've got this big peak at about 130 hertz. This big peak at about 130 hertz. Now, I think that's slightly shy of this third order room mode, which is at 150. So it should be around here is where it's predicted to be at, but it's around 130. So I'm not sure if my dimensions for the room are exactly spot on. Maybe it's a little bit longer, a bit shorter, but the 35-36 stacks up pretty well. It's just this room mode seems a little bit shifted down. So I'm curious if I can get a null, so one of these null figures on the X-axis to be about 140, if I can sort of just pull this one down here. So let's see what X-axis position will produce a 140 null. So let's make this 60 hertz, 60 centimeters, sorry, from that back wall. I'll measure that out and I'll test it. Let's try this. What I'll do is I'll just duplicate. Let's make this 60. And yeah, let's see if that null helps with this. Maybe not 143. We'll make it a little bit further away. Let's go 55. No, a bit further away. Sorry. Has to be about 130 because that's where that peak is. If we look down there, 130, 65 hertz. So I'm just pushing it back closer towards the wall, about 5 centimeters. Got my trusty measuring tape. Let's see if this checks out. I'll make triple check my distances. Should be, see, that's 70. Oh, actually, you know what? That original measurement was out. So I'm just going to quickly correct that. Let's go here. That was actually 80 centimeters. So let's go, we're going to be at 65. So I'm going to move it back about 15 to 65. About to there. All right, let's shift it back. See if this produces something that's a little bit of a better response. Okay. All right, so what I've done is for my first test is, I'm just going to rename this. So what I've got is I've moved that speaker back to 65 centimeters on the Y-axis from the front wall. So I have a stronger dip around where that current peak is. Maybe this will work, maybe it won't. Let's actually see. So the peak originally was at 104 decibels and the trough was at 89. So that's 104 to 89, that's 15 decibels of difference. Now by moving that speaker in, we're at 99 decibel peak there, and the trough is 88. So 88 to 99, that's 12 decibels. So that's improved that response at that peak by 2 decibels by just shifting it there. Now I'm curious because it's quite hollow in this low range here around 90 hertz. If we can get a bit of a peak or something happening there from this distance to the sidewall. So what I'm going to do on the Y-axis, so I improved this sort of room mode that was here by shifting that x-axis, the speaker closer towards the wall. Now let's see if we can do this with the y-axis. Let's just shift you over. Let's go y-axis. It's B-I-R-Y. What are we going to change here? So it's currently 143. So this y-axis has a null at 60 hertz, which we sort of get around here. It just starts to dip down, and at 180. Let's see if that's reflected here. 180, not really. The dip is more up here at 200. And a peak at 120, which is sort of, that's actually exacerbating that. Oh, no, not really. Yeah, it is 130. It's peaking at 120, so that y-axis position of the speaker isn't quite helping that there anyway. So if we can get like a peak at 90 hertz from this, let's just bring that speaker slightly in. So go 160. 170. Gives a 100 hertz boost. So you get a boost around here. Oh no, yeah, boost around there and then null around there. Might just work. So what do we need to be at? 170. What were we currently before? 143. Okay, that didn't perform. So that didn't perform as I hoped it to, or as well as I had hoped it to, because I also got to remember that these nulls and peaks, number one, I can't measure to a millimeter accurate, and number two, this comb filtering isn't precisely super narrow Q dip or not. I actually don't know how it is. So look, this one here, it did perform well. It did perform better than the original one, but there's still just as much variance here as there was previous, like not as there was. Actually, you know what? There's the exact amount of variance as there was bottom to top. So moving that y-axis in that close didn't produce a desirable effect, period, whatsoever. So this y-axis, which was a y-axis for 170 centimeter boost at 100, or null boost 100 hertz, did not work. Did not work. So I'm going to move that y-axis back to where it was, and then maybe contemplate how I can change it or make it a little bit better, because that just didn't work, that y-axis one at all. All right, so now we've got this x, y, and z axis. Moving the x-axis alone really improved the response a lot. Now this y-axis one though, I don't know. We're going to figure out something to do with this y-axis that could possibly do better. Do we try and chip away at this room mode even further, this 130 hertz? I don't know. Do we? Let's see. Fucking roll. Let's try and do this. 120. Let's try that. Let's try 120. Fuck, I have no clue. So, at the moment, I have no fucking clue, because the x-axis movement was the best. This y-axis movement did 2 bits of fuck all. So, let's just try this out. We'll see. Yeah, nah, that is not good. That is not, like, it gets at 120 hertz into that range, but what does it do here? Completely causes a super dip around 80 hertz. At 70 hertz gets attenuated. I don't know if I like that, because that's just made that difference between there and there much more, although that is more flat than 100 hertz moving into there. Do I like that? I don't know. I do not know, because that's a potential contender. Let's go y-axis 120. I don't know if that's a good thing what's been done here. Let's just go 1/24 smoothing, because it's definitely, like, from that 100 hertz up, there's very little deviance. 94, 100, that's plus minus 3. That's really solid from 100 hertz up, but then it does tail off and drop off, which I don't know is a good thing, and that highest peak there. So I reckon that's it. I reckon that's what we're going to end up with. X65, Y143, Z125. Because this one here, let's just put that one back on. It just dips too much there. This one here, it's good, but again, it just dips way too much. It's pretty controlled though. Between there, but we're talking 1 decibel there. I'd rather have a little bit more energy at 70 hertz, a couple more dB at 70 hertz, and then it even out as it goes up. So what did we learn? That having some theory behind what we're doing is good, but also relying on it too much isn't. So because my first move was just to move that back on the x-axis based on the first measurement and the calculation, and that ended up being the best result. All the subsequent ones were obviously you're limited by space in terms of how far can you move the speaker close or further away from the wall, because you also got stereo imaging to consider, and also the fact that not all the time you'll put something in, predict it, and that'll operate exactly or it'll measure exactly as you hope. So this is why it's sort of like trial and error, at least for me it is, and it's an interesting result. So simply by moving my speaker back, what was it? It was originally, the original position was 80 centimeters from the front wall to 65 centimeters from the front wall. So there's still a bit of distance there. I do have, it's quite a large monitoring triangle I have because I've got the space in this room to do that. So it's 65 centimeters away from that wall. It improved the response dramatically by the tune of 2 decibels at that room mode or peak there. Now, I got something for you. Okay, so what I've got here is for next week. It's called Filama. And Filama is actually a construction material they use to isolate things like concrete slabs. And the data on it is incredibly detailed. And we're going to use this product for our speakers to test if something like this is actually a better isolation tool than commercial retail isoacoustic ones, which I have, because I couldn't find any data on them, but I can find a lot of data on this, and we can go through it and do some performance testing on waterfall plots to see if this outperforms the isoacoustic stands. Will be interesting to see.